ChatGPT, Claude, Gemini, Llama. These AI models are everywhere right now, and they're blowing people's minds. But where they come from, and what makes them so good at understanding and generating human-like language? In this video, we'll explore the history of large language models, or LLMs, from the first chatbot to powerful models like ChatGPT and Claude, and discover how they evolved to understand and generate human-like language so effectively. First off, let's talk about how language and intelligence are linked. Take a simple word like hat. When you hear it, each of us would have a different picture in mind. It could be this, or maybe even this. But there's a common thread tying all these ideas together. That ability to store and process concepts in context is a key part of intelligence. Language is one of the things which set apart humans in intelligence. Other primates like monkeys have the ability to see actions and repeat them and learn from each other in that manner. The advent of language allowed the expression of any action, an imagined action or a series of thoughts. Language enables us to communicate complex ideas, share knowledge across generations, and collaborate on a massive scale. It's the foundation of our culture, science, and technology. So when we talk about creating intelligent machines, being able to understand and generate human language is a crucial piece of the puzzle. Let's rewind to the 1960s, when a guy named Joseph Weizenbaum at MIT created Eliza, the first ever chatbot. Eliza was designed to mimic a psychotherapist. Using pattern matching and substitution, the idea was to create a program that could engage in a conversation without needing a deep reservoir of knowledge, like current LLMs. Eliza worked by analyzing user input for keywords and phrases, then generating responses based on predefined patterns. For example, if a user mentioned words like girlfriend, depressed, or mother, Eliza would provide a relevant response. If the program couldn't find a suitable pattern, it would fall back on generic responses like, please go on, that's very interesting, etc. Let's try out Eliza in a demo which is available online still. So, hi, it's nice to be chatting with you. Okay. Mm. I'll I'll tell Eliza like I'm a bit sad today. I really am not sad today. I'll still do that. Okay. Mm. It's the morning. That's not really an issue. Now you can see that these responses are quite generic. They don't really understand what we are saying. Even if I said some other answer, probably they would have given the same response. Despite its simplicity, Eliza had a surprising impact on users. Please note that this was in the 1960s again. Many people who interacted with the program became emotionally attached, sharing personal problems and seeking advice as if they were talking to a real therapist. This phenomenon, known as the Eliza effect, demonstrated how easily people could attribute human like qualities to a computer program. However, Weizenbaum was troubled by this tendency to conflate a simple program with genuine human interaction. He believed that there were aspects of human life, such as love and loneliness, that computers could never truly understand. Weizenbaum also became a vocal critic of rapid advancements of artificial intelligence. Fast forward a few decades, and the advent of deep learning brought about a new class of AI models called recurrent neural networks, or RNNs. Simple artificial neural networks, like a feed-forward neural networks, already existed by this point. And RNNs, unlike traditional neural networks, have a kind of memory that allows them to process sequential data, like the words in a sentence, while maintaining context from previous inputs. This made them a natural fit for language modeling tasks. RNNs can handle sequential data effectively, including text, speech, and even time series. They can process inputs of any length, unlike feed-forward neural networks. RNNs also share weights across time steps, enhancing training efficiency. However, standard RNNs can sometimes struggle with capturing long-term dependencies, which means that they have difficulty connecting information from much earlier in the sequence to the current input. To address the limitations of standard RNNs, researchers developed a more sophisticated architecture like long short-term memory, LSTMs, and even gated recurrent units, GRU. These architectures introduce special mechanisms to help the models better capture and remember the important information over longer sequences. LSTMs use a series of gates to control the flow of information into and out of the memory cell. It wasn't just paying attention to all the previous inputs, it could control which previous outputs or activations it had access to. This allows the model to selectively remember or forget information over long sequences, helping it maintain context more effectively. GRUs, on the other hand, simplify the gating mechanism used in LSTMs, while still achieving comparable performance on many tasks. They require fewer parameters than LSTMs, which can make them easier to train and more efficient. The introduction of LSTMs and GRUs was a significant milestone in the development of language models, as these architectures laid the groundwork for the powerful language models we have today, like ChatGPT. They enable models to capture long-range dependencies and context, which is crucial for understanding and generating coherent language. If you're curious to learn more about RNNs, LSTMs, and GRUs, since we are not diving too deep into these topics over here, we'll be leaving some links in the description below where you can dive deeper into these architectures. In 2014, the attention mechanism burst into the scene and changed the game. The attention mechanism allowed models to dynamically focus on different parts of the input sequence when generating each output, enabling them to capture complex relationships and dependencies in language data. This was a huge leap towards human level performance in things like translation and summarization. Building on the success of attention, researchers developed a new architecture called the transformer, which relied entirely on self-attention mechanisms to process input sequences. Don't worry about the technical terms as much right now. We will go into depth about transformers, self-attention, etc. later on. By allowing each element in the sequence to attend to every other element, transformers were able to capture even richer and more nuanced patterns in language. In recent years, researchers have pushed the boundaries of language models by training ever larger models on massive amounts of text data. These large language models, or LLMs, can have billions of parameters and exhibit remarkable abilities to understand and generate human-like language across a wide range of tasks. Models like GPT-4, Palm, Cloud, etc. have achieved top performance on benchmarks like question answering, summarization, and even open-ended conversation. From Eliza to large language models powering ChatGPT and other LLMs, language models has come a long way. As we keep pushing the limits of what's possible, we're getting closer and closer to creating AI that can understand and use language just like humans do. In the rest of this course, we'll explore the inner workings of these remarkable models in greater detail, covering concepts like transformers, vector databases, and retrieval augmented generation, or RAG. We'll also get some hands-on experience with some of the latest tools and frameworks for building cutting-edge language AI applications. So stick around, there's plenty more to learn.